Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today, going to take a topic electrostatics in the subject EMFT, electromagnetic field theory, which is studied or taken up in the B.Tech Electronics and Communication fourth semester. Before starting to the EMFT concepts in the theory, I would like to introduce the basic concepts related to the electrostatics. So, what do you mean by the electrostatics? The word electrostatics means study the charge at rest. When the charge is at rest, you need to study the properties of the charge at rest and various topics related to the electrostatics, that is, electric field of lines, electric field, electric potential, dipole moment, and many more topics under the electrostatics. Uh, so, First of all, introduction to electromagnetics. Electromagnetics is the branch of physics in which electric magnetic fields and interaction of electric magnetic fields are studied. Applications of electromagnetics. The various applications of electromagnetics include microwaves, antennas, electric machines, satellite communication, bioelectromagnetics, electromagnetic interference, and compatibility. Electromechanical, nuclear research, fiber optics, energy conversion, and remote sensing. Advantages: for melting, surface hardening, and for soldering operations, electromagnetic fields are used. Electromagnetic energy is used in agriculture to change the taste of vegetables by reducing acidity. Electromagnetic devices. Electromagnetic devices. The various electromagnetic devices include transformers, electric relays, TV, radio, telephones, electric motor, transmission line, antennas, optical fibers, radars, and lasers. The designs of these devices requires through knowledge of the laws and principle of electromagnetics. Now, electrostatics. First, introduction about the electrostatics. The basic definition of atom, then electric charge. What do you mean by the electric charge? Properties of electric charge. What are the various methods of charging? What do you mean by state the Coulomb's law? Electric field. Then electric line of force, electric flux, electric potential energy. What do you mean by electric potential and the potential difference? In the last, we are going to take about some questions and quizzes related to the electrostatics. Introduction to electrostatics. Electrostatics is the branch of physics in which the static electric field produced by static electric charge are studied. Electrostatics plays a major role in everyday life. The various applications of electrostatics include photocopiers, defibrillators, paint spraying, electrostatics precipitators, etc. The computer peripheral device include liquid crystal display, that is LCD, keyboard, touchpad. Works on the principle of electrostatics. Electrostatics used in the agriculture activities like spraying through the plants, shorting seeds, etc. Electronic components such as capacitors, resistors, etc. function based on electrostatics. History of electrostatics. The natural phenomena of static electricity has been known since ancient times. The credit of discovery the credit of discovery the credit of discovery of static electricity goes to Thales of Milesius around 600 BC. Thales noticed that amber rubbed with wool or cloth attracts lighter objects. Or when a glass rod is rubbed with silk or an ebonite rod is rubbed with flannel, these requires power to attract light bodies such as small pieces of paper. The agency which gives this attracting power is called electricity. The bodies which acquire this power are said to be electrified or charged. The electricity produced by friction is called frictional electricity. If the charges in a body do not move, then the frictional electricity is also known as static electricity. So, according to the historical development, the Greeks knew something about electric force arising from frictional electric charges. This was as early as 66th century BC. One of the founding father of Greek science, Thales of Miletus, observed that amber, when rubbed with wool, is capable of attracting bits of straw. The science of electricity has its roots in this observation. Electron is the Greek name for amber. Here, electron, Elektron, is the Greek name of amber for amber. This is the origin of the words electric charge, electric force, electricity, and electron. You should have noticed that just after you have combed your dry hair with a plastic comb, the comb acquires the ability to attract small pieces of paper. This is of course truly or true only if there is no humidity in the atmosphere. The ancient Greeks also knew that rock, that is lodestone or magnetite iron ore from the islands of Magnesia in Asia Minor could attract small pieces of iron. The ancient Chinese observed that if a thin, long pieces of roughly in a north-south direction, it was around 1000 AD. The Chinese made use of magnetic compass. Gilbert gave the first scientific account of the early experience of electric and magnetic effects. He introduced the name electricia or electrica for substance like amber, which, when rubbed with suitable materials, attracted light bodies. He stated that while electric charge of the same kind repel each other, those of opposite kind attract each other. The two kinds of electricity were named as resinous and vitreous. Vitreous, resinous, and vitreous. The kind of electricity developed on amber when it is rubbed with wool was called resinous, probably because amber is a resin. The type of electricity developed on wool was vitreous. An American scientist statesman, Benjamin Franklin, 1706 to 1790, introduced a convention according to which the kind of electricity that appears on the glass will be called positive, while that on ebonite or amber, when rubbed with wool, will be called negative. So vitreous become positive while resinoids become negative. This convention has ever since been followed. So for many years, Greeks thought that this phenomenon is due to the unique property of amber. What Thales noticed is nothing but the static electricity. The word electricity is taken from the Greek word electron, which means amber. Okay. In normal state, all atoms in an object contain equal number of electrons and protons, as we know about the atomic theory. However, when one object is rubbed with other, few electrons from one object will move to other. The object that receive extra electron has more number of electrons than proton, so it becomes negatively charged. Similarly, the object that donates electrons loses few electrons and has less number of electrons than protons, so it becomes positively charged. Now, this is the small concept or small theory related to the atoms. Atoms are the basic building blocks of matter. Atom consists of three sub atomic particles. They are protons, electrons, and neutrons. Electron is negatively charged particle, proton is a positively charged particle, and neutron is a particle that has no charge. The strong nuclear force between protons and neutrons stick them together to form a nucleus. Neutrons in the nucleus have no charge, so the overall charge of nucleus is positive. We all know about the atomic theory. So now electric charge. So Benjamin Franklin was the first American scientist who proved that there are two types of electric charge, positive charge and negative charge. Electric charge is a property of subatomic particles, particularly includes electrons and protons. Electrons have negative charge, protons has positive charge, and neutrons do not have any charge. The charge of electrons and protons is measured in coulombs, represented by C. Electron has a charge of minus 1.602 into 10 to the power minus 19 coulombs, and proton has a charge of plus 1.602 into 10 to the power minus 19 coulombs. The charge of an electron is equal to the charge of proton. However, electron has a negative value of charge and proton has positive value of charge. Generally, the number of electrons and protons in the atoms are equally numbered. Due to opposite charges of electrons and protons, the charge get cancel each other and the atom remains neutral. However, if the atom has unequal number of electrons and protons, then the atom is said to be charged atom. If the atom has more number of electrons, negatively charged, than protons, positive charge, then it is said to be negatively charged. Similarly, if the atom has more number of protons than electrons, then it is said to be positively charged. Now, these are just some properties of electric charge. The various properties of electric charge includes additive or additivity of charges, conservation of charges, and quantization of charges. So, additivity of charges. If a system contains 2 point charges Q1 and Q2, then total charge of the system is obtained by simply adding Q1 and Q2, that is charge add up like real numbers. If a system contains n number of charges Q1, Q2, Q3, Q4 dash 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 Qn, then total charge of the system is Q1 plus Q2 plus Q3 plus Q4 plus dash 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 plus Qn. Charge is a scalar quantity. Charge is a scalar quantity. That means it has magnitude only, not any direction. It has magnitude but no direction, similar to mass. However, there is one difference between charge and mass. Mass of the body or body is always positive, whereas charge can be either positive or negative. Let us take, for example, the system containing 4 charges. Q1 equals to 2 Coulomb, Q2 equals to 3 Coulomb, Q3 equals to minus 3 Coulomb, Q4 equals to 4 Coulomb. Then the total charge of the system is equals to the algebraic sum of all the charges. So 2 plus 3 minus 3 plus 4, this come out to be 6. Therefore, the total charge of the system is plus 6 Coulomb and it is positively charged. Now, conservation of charge or conservation of electric charge, charge is conserved. So, the law of conservation says neither the anyone is created nor be destroyed, or we can say that it is transferred from one object to another. So, the law of conservation of charge states that charge cannot be created or destroyed. However, the charge can be transferred from one object to another. Electric charge, quantity of electricity is conserved in the same manner as linear momentum, energy, angular momentum, etc. The law of conservation of charge is the basis of many equations of electricity and magnetism. According to the law of conservation of electric charge, the algebraic sum of positive and negative charges in an isolated system remains constant. In other words, the net charge of an isolated system remains unaltered. This law, like the laws of conservation of energy and momentum, is one of the fundamental laws of physics. There are no exception to this law and it is universal. Conservation of charge does not mean that charge cannot be produced or destroyed. It simply means that if ever charge is created or destroyed, it will always be in equal and opposite amount. As discussed earlier, when two bodies are rubbed, we get simultaneously two unlike charges of equal magnitudes. Uh, for example, the conservation of charges can be illustrated by some example. When a glass rod is rubbed with silk, negative charge appears on silk while an equal amount of positive charge appears on the glass rod. In this way, the net charge on the glass silk system remains zero both before and after rubbing. The following, or we just take the some example related to the nuclear reaction. And in the nuclear reaction, we know that the chemical reaction takes place and law of conservation holds there. So these are the some examples of uh, conservation of charges. Now, I would like to state some comparison between charge and mass. It is a charge has an important role in electromagnetism, and mass has important role in gravitation. Charge can be positive and negative, whereas mass is always positive. The electric charge is independent of the velocity of the body. According to the special theory of relativity, the mass of the body increases with velocity of the body. If I'm talking about the charge, the net charge of the system remain conserved in all inertial frames of reference. That is, net charge of a system is relativistically invariant, whereas mass is not conserved by itself in relativistic processes. So we can say that uh, let us consider two objects, object A and object B. Such object A has equal number of electrons and protons, so it is electrically neutral. Similarly, object B has equal number of electrons and protons, so it is also electrical neutral. Object A and object B, as shown in the figure, yes, object A is having number of electrons equal to number of protons. Object B now when we just close closely or bring both the objects near to each other, the sum of the negative charge moves towards the object B and it will become more negative, and it can be said that it is negatively charged, and the positive charge will remain in the object A in more quantity, so we can say that it is positively charged. When object A and object B are rubbed with each other, negative charge from object A can be transferred to object B. Hence, object B has more number of electrons than protons due to gaining of extra electrons. Similarly, object A has lesser number of electrons than protons due to losing of some electrons. Therefore, object A becomes positively charged and object B becomes negatively charged. However, the total charge of an isolated system remains constant. Now, quantization of charge. Quantization, the charge of any object is equal to the integer multiples of elementary charge. This is known as the quantization of charges or charge. It is given by Q equals to N. During Benjamin Franklin time, the electric charge was considered to be continuous fluid. Continuous fluid. This idea served many purposes. However, atomic theory of matter showed that fluids themselves are not continuous but are made up of some atoms and molecules. It was in 1897 that J.J. Thomson discovered the electron. It was in 1911 the Millikan successfully showed that charges on tiny oil drops are exactly multiples of elementary charge. Nowadays, We know from a number of experiments the electric fluid is not continuous and all the charges occurring in nature are positive or negative integral multiples of certain minimum electric charge. This minimum electric charge is the magnitude of electric charge on an electron. This fundamental charge, to which we give the symbol E, has the magnitude of 1.60 into 10 to the power minus 19 Coulomb. So the charge on electron is minus E, while the charge on the proton is plus E. Okay. The fact that charges on proton and on the electrons are numerically equal but opposite in sign has been checked experimentally to an amazing degree of accuracy, and namely to 1 part in 10 to the power 20. Any charge q, no matter what is its origin, is given by q equals to plus minus ne, where n is equals to the number of integer or stand for the integer value, that is 1, 2, 3, 4, and so on. When a physical quantity such as electric field, electric charge exists in discrete packets rather than in continuous amount, it is said to be quantized. This fact is referred to as quantization of electric charge. So I'm repeating that when a physical quantity such as electric charge exists in discrete or packets rather than in continuous amount, it is said to be quantized. This fact is referred to the quantization of electric charge. When suitably examined on a microscopic scale, most of the properties such as mass, energy, angular momentum, etc. are observed to be quantized. The property of quantization of electric charge has to be kept in mind while dealing with electric and magnetic problems at microscopic level. For many practical purposes or large-scale phenomena, we can ignore the quantization of charge and regard the charge as something continuous. In the discussion of classical electricity and magnetism, the quantization of charge is completely ignored. This is because of the quantum of charge E is so small that graininess of electricity does not show up in large scale experiments, just as while breathing we do not feel that air is made up of atoms. Just as Newtonian mechanics does not correctly describe the behavior of matter on an atomic scale, the classical theory of electromagnetism also fails to describe the behavior of charge on the atomic scale. So, we simply say that q equals to ne, where q is the electric charge of any object or body, n equals to any integer positive or negative, where minus e is the elementary charge carried by the single electron, or e is the elementary charge carried by the single proton. The charge on electron is written as minus e, and this is positive. The quantization charge first suggested by the experimental laws of electrolysis discovered by Faraday. It was experimentally proved by Millikan oil drop experiment. The total charge on object is equal to the algebraic sum individually present within the object. If an object contains n1 electrons and n2 protons, then total charge on the object is n1 into minus e plus n2 into e. For example, if the object contains 150 electrons and 200 protons, then the total charge on the object is minus 150e plus 200e is equals to 50. Hence, the object is positively charged. The object charge can be exactly 0e or 1e or 2e dash 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 or minus 1e minus 2e, but not in fractional value, that is 1 by 2, 1 by 4, and so on. Next. Now, these are the some methods of charging. The process of supplying the electric charge, that is electrons, to an object, or losing the electric charge, electrons from an object, is called charging. So the process of supplying electric charge, basically the electrons to an object or losing the electric charge, electrons from an object is called charging. An uncharged object can be charged in different ways: charging by friction, charging by conduction, charging by induction. So these are the three basic fundamental methods of charging. By friction, that is by rubbing, you can charge or transfer the electron, or by charging by conduction method, or by charging through the induction method. Now let us discuss each methods of charging one by one. Charging by friction. When object is rubbed over another object, the electrons get transferred from one object to another. This transfer of electron takes place due to friction between the two objects. The object that transfer electron loses negative charge electrons, and the object that accept electrons gain negative charge, that is electrons. And the object that gains the extra electrons become negatively charged, and the object that loses electrons become positively charged. Thus, the two objects get charged by friction. The charge obtained on the two objects is called friction charge. This method of charging an object is called electrification by friction. Now, the charging by conduction. The process of charging the uncharged object by bringing it in the contact with another charged object is called charging by conduction. That means basically the conduction, you just bring any charged object to the uncharged object in contact with the uncharged object. So the charge start transferring from the charged to uncharged. It's just simply like you may call it as a diffusion, or anything which is at higher density uh, moves towards the lower density, or we can call that, suppose if you spray a perfume in a room from one corner, so that perfume spread to the another corner, because there is a low density. Wherever the low density is there, the fumes or the fragrance of the perfume moves on through the medium of air. Similarly, charging by conduction is the same process. When you bring any charged object with uncharged object in contact with uncharged object, the charge start transferring, and this process is known as charging by conduction. A charged object has unequal number of negative electrons and positive charges, protons. Hence, when a charged object is brought in contact with uncharged conductor, the electrons get transferred from charged object to the conductor. Consider an uncharged metal rod A capped on an insulating stand and negative charge conductor B as shown in figure below. This is the figure in which one rod is insulating on a insulating stand, which is totally uncharged, and rod B is charged with negative charge. When you just make rod B in contact with rod A, the charge will equally get distributed or transferred to the rod A. So this is called the charging method by conduction. If we touch the uncharged conductor A with the negatively charged conductor B, transfer of electrons from charged conductor to uncharged conductor takes place. Hence, uncharged conductor gains extra electrons and charged conductor loses electrons. Thus, uncharged conductor A becomes negatively charged by gaining of extra electrons. Similarly, uncharged conductor becomes positively charged if it is brought in contact with positively charged conductors. Now, the third is the charging by induction. This is very important. The process of charging the uncharged object by bringing another charged object near to it, but not touching it. It is called charging by induction. That is, influence. By the influence of anything, if we are going to deviate or divert, then we can say that due to the induction. Consider an uncharged metal sphere and negatively charged plastic rod as shown in the figure in the next slide. If we bring the negative charged plastic rod near to the uncharged sphere as shown in figure below, the charge separation occurs. This is the phenomena of charging through induction. In figure first, plastic rod and the sphere is separated with a distance, and if we just bring a plastic rod more closer to the sphere, the negative charge in the plastic rod attracts the positive charge of the sphere towards it and repel the negative charge towards another side. And in figure third, if you just ground the sphere, the whole negative charge moves to the ground and the sphere will become positive, fully positive charge. And again in the fourth figure, you just again separate both the rod and the sphere. The positive charge in the sphere get attracted towards the plastic rod and move to one end of the sphere that is closer to the plastic rod. Similarly, negative charge get repelled from the plastic rod and move to another end of the sphere that is farther away from the plastic rod. Thus, the charges in the sphere rearrange themselves in a way that all the positive charge are nearer to plastic rod, nearer to plastic rod, and all the negative charge are farther away from it. If this sphere is connected to a ground through the wire as shown in figure, free electrons of the sphere at farther and flow to the ground. Thus, the sphere becomes positively charged by induction. If the plastic rod is removed, as shown in figure 4, all the positive charge spread uniformly in the sphere. Next, now we are starting with Coulomb's law. Coulomb's law yes, Coulomb's law, the study of electrostatics begin with the Coulomb's law. The study of the electrostatics began with the Coulomb's law. Coulomb's law is an experimental law published in 1785 by French physicist Charles Augustin de Coulomb. Uh, Charles Augustin de Coulomb. Uh, just wait a minute. There's some problem. Yes, the study of electrostatics begins with the Coulomb's law. Coulomb's law is an experimental law published in 1785 by French physicist Charles Augustin de Coulomb. This law is very important for the development of theory of electromagnetism. Uh, Charles Coulomb observed that Charles Coulomb observed that when two electric charges are placed close to each other, they experience a force. He used a torsion balance to measure the repulsive and attractive force between the charged particles. So the statement of Coulomb's law: Charles Coulomb has developed the two laws on the basis of his experiment, which are known as Coulomb's law of electrostatics. First law: Coulomb's first law states that two charged particles of same charge, positive and negative, will repel each other, and two charged particles of opposite charge, one positive, one negative, will attract each other. Okay. Second law, Coulomb's second law states that the force of attraction or repulsion, between the two electrically charged particles is directly proportional to the product of magnitudes of two charges and inversely proportional to the square of the distance between two charges. This force of attraction or repulsion between two charges is also depends on the medium in which the charge are placed. So electric charge is a scalar physical quantity which determines the interaction between the charged bodies. Coulomb's law, discovered in 1785, deals with this electric interaction. This law is analogous to Newton's law of gravitation. Coulomb's law was discovered by Cavendish, but this fact became more known only after 65 years of his death. According to the Coulomb's law, electrostatic force of interaction between two-point electric charge is directly proportional to the product of the charges, inversely proportional to the square of the distance between them, and acts along the straight line joining these two charges. Strictly speaking, Coulomb's laws apply to the stationary point charges. If two-point electric charges Q1 and Q2 are separated by distance d, then the electrostatic force between the two charges is given by force is directly proportional to Q1 and Q2 upon d square, or we can say that electrostatic force is equals to proportionality sign is removed by constant k into Q1 Q2 upon d square, where k is a positive constant of proportionality called electrostatic force constant or Coulomb's constant. Its value depends upon the system of units and also on the medium between the two charges. If the point charges are in vacuum, then I'll show in the next slide. If we increase the distance between the two-point charges, that force of attraction or repulsion present between them will decrease. In the similar way, if we decrease the distance between two-point charges, the force of attraction repulsion between them will increase. Coulomb's law can be mathematically written as, I had already, proportionality sign is replaced by k, which is known as Coulomb's constant, k, and its value is depending upon the medium. So, where F equals to the force of attraction or repulsion between the charges, Q1, Q2 is the magnitude of charge first and charge second. D is the distance between the two charges. K equals to the constant whose value depends on the medium in which the charges are placed, and K is given as 1 by 4 pi epsilon, where epsilon equals to E naught into ER. So it can be also written as K equals to 1 by 4 pi E naught ER, where E naught is known as the permittivity of vacuum, that is equals to 8.854 into 10 to the power minus 12 F by M, or ER is the relative permittivity of the medium with respect to free space. Okay, so E naught epsilon naught is the permittivity of vacuum, and its value is 8.845, and ER is the relative permittivity of medium with respect to free space. For vacuum, the relative permittivity ER equals to 1. Hence, permittivity is equals to E naught. Therefore, the force of attraction or repulsion between two electric charges that are placed in vacuum and medium is given by, in vacuum, it is given by force equals to Q1 Q2 upon 4 pi epsilon naught d square. Or in any medium, it is represented as force equals to Q1 Q2 upon 4 pi epsilon naught ER into d square. Now, before moving to electric field, that is the next topic, in continuation to the Coulomb's law. Coulomb's law in vector form having the great importance. So, as we know that the like charges are attracting each other, and unlike charges are attracting each other, like charges are repelling each other. Consider 2 point charges q1 and q2 separated by some distance d. If the product of the magnitude of charge is greater than 0, that means both are positive, or if the product are negative, then the charges repel each other. On the other hand, if we say that the product of two charges is less than 0, charges are dissimilar, then the charges attract each other. So, as we know, the force is a vector quantity. So, the electrostatic force, or the Coulomb's law, or that is given as force equals to K Q1 Q2 upon R square, is a vector quantity, and by calculating the resulting force, keep the vector theory very clear in mind, because whatever the resultant force, we have to mention the direction of the resultant force when a system of charges are um, taken up. And if we ask to find out the what is the charge, or what is the force on the one charge due to all of the charges and the resulting direction of the forces, then the vector theory must be very clear to us for calculating the force. The SI unit of charge is Coulomb. Now, if you had gone through the gravitational field or gravitational forces or gravitational theory, we find the formula of electrostatic force and the gravitational force is almost similar. In addition to the electrostatic force between two charged bodies, there are also exists a gravitational attraction between them. Uh, so, points of similarity while doing the comparison of electrostatic and gravitational forces, both these forces are central forces. That is, they act along the line joining the centers of the two interacting bodies. Both the forces obey inverse square law of distance, as you had seen in the formula. Both are conservative forces, that is, the work done by them does not depend upon the path followed. Both the forces can operate even in vacuum. Now, points of dissimilarity. While the gravitational forces are always attractive in nature, the electrostatic force may be attractive or repulsive. While the gravitational force does not depend upon the medium, the electrostatic force definitely depends upon the medium. Electrostatic forces are extremely large as compared to the gravitational force. The fact that electrostatic forces are much stronger than the gravitational force is clearly revealed from the following illustrations, or some illustrations which we'll see later on. Now, starting with the topic, that is electric field. Electric field, the region around a charged particle within which other charged particle will experience an electrostatic repulsive or attractive force, is called electric field. Electric field is also called as electrostatic field. The electrostatic force or electric force is exerted by the static electric charges, that is electrons and protons. Next, so electric field, as you see in the pictorial representation of the charge, that is positive charge and negative charge is showing to you in the diagram, and the rays are moving perpendicularly away or towards the charge. So we can say these moving lines which are in the perpendicular from the charge are known as electric field of lines. Okay, so now the electric field strength, the strength or intensity of the electric field at any point within the electric field is called electric field strength. To describe an electric field, we must specify its strength. The strength of electric field at any point within the electric field is determined by placing the unit charge at that point. When the unit charge is placed in electric field, it will experience an electric force. The electric force is either attractive or repulsive. The amount of electric force acting on a unit charge placed at any point within electric field is called electric field strength or electric field intensity. So, more specifically, we can say that there is region of space around a charge of a system of charges within which other charged particles experience electrostatic force. This region is spoken as electric field. Thus, a particle is said to be in an electric field if the particle experiences a electrostatic region. Theoretically, theoretically speaking, the electric field extends up to infinity, but practically, the electric field does not show detectable influence beyond a certain limited distance. The electric field strength or field strength or electric field intensity or electricity is the ratio of the electric force exerted or experienced by a positive charge particle to the magnitude of the charge Q naught on the particle. So we can say mathematically E is equals to force upon Q naught. Since Q naught has been taken to be positive, therefore the direction of electric field be the same as that of force. So we can conclude that electric field intensity is also a vector quantity. It is also clear from the definition of electric field that electrostatic force on a negative charge particle will be in the direction opposite to that of the field strength. It is further clear from the definition that electric field intensity is a vector quantity whose magnitude and directions are uniquely determined at every point in the field. Thus, electric field is a vector point function. It must be clearly noted that electric field is external to the test charge. That is, electric field is neither the field produced by the test charge nor it is supposed to include any contribution from the test charge. In fact, electric field exists whether some test charge is placed in the field or not. So, we can say that if the amount of force acting on a unit charge at a given point is less, then electric field strength at that point is less. In the similar way, if the amount of force acting on a unit charge uh, on a unit charge on a unit charge at a given point is high, the electric field strength at that point is high. Electric field strength or intensity is a vector quantity. It has both magnitude and direction. Electric field strength can be mathematically defined as force per unit charge. As we know that force is measured in newtons and charge is measured in coulombs, hence electric field strength is measured in newtons per coulomb. Types of electric field. So there are basically four types of electric field. The electric fields are of four types: uniform electric field, non-uniform electric field, static electric field, time varying electric field. Uniform electric field. Uh, so I would like to continue this lecture, the types of electric field or the particular topic that is types of electric field in the next lecture. Uh, till to now, thank you. Thanks a lot. Have a nice day.